Any questions about op amps, DFAMs, anything about op amps till now? Okay, so today is the last class, so let's try to wrap it up as quickly as possible. The plan for today's class is to cover some of the topics which I'm sure you are familiar with, but we didn't have time to cover in this course, right? So couple of those topics are quite important. So let me go through it in a structured manner, then we'll wrap it up at in the last 15-20 minutes. So tell me, what was the reason we wanted to go towards a two-stage structure when we had this, let's say, common source amplifier, right? So let's say I have instead of putting this resistive load, I'm putting an active load. And this is biased, and so on. And this is also biased. So what was the reason I wanted to put another stage here? I mean, in case of a common source amplifier or in case of a differential amplifier, we put two stages. What was the reason? If for differential amplifier, yes, we want a differential input, but that is not two stage, right? Differential input can be a single stage. Yeah, for high gain, right? So what was the reason why we couldn't get high gain? One of the reasons was if we had to drive a resistive load, right? If we had to drive a resistive load, then if we connect this load directly to the output of the first stage, the gain will drop because the effective output impedance drops, right? So in certain cases, you don't have to drive a resistive load. For example, in this current structure, you see, the first stage is driving a capacitive load. First stage is driving the second stage, which is essentially a capacitive load, right? You see the CGS of the second stage. So it's not directly seeing RL. So does it, which essentially tells us that RL is not directly loading the first stage. That is why the second stage was there. Now, what I am essentially asking is, what limits the gain of the first stage? What will be the first stage gain? GM times? Right, so there are two transistors, M1, let's call it M1, M2. So let me get rid of the second stage because we're not talking about it anymore. So the gain of the DC, at least the DC gain of the low frequency gain is minus GM1 by G01 plus G02 or GDS1 plus GDS2, right? So this is the gain. Now, if I have to increase the gain, we know a few tricks, right? We can increase the W and the L simultaneously. By the way, in this case, let's say I keep W by L same, okay? And I want to bias it with a constant current source. I can bias, multiple ways of biasing using constant current source. So let's say this is the structure that I chose. Okay. So now tell me whether the gain, I want to increase the gain by only changing I0. Should I increase I0 or should I decrease I0? Why? GM will increase. What happens to GDS? So now, since both are increasing, I need to understand the rate. So at what rate does GM increase? Under root I. At what rate does GDS increase? Proportional to I. So what should I do? How does the gain vary? right? The gain decreases if I increase I naught, right? So if I have to increase gain, I have to decrease I naught, right? So this is sometimes a bit counterintuitive if you are seeing it for the first time. It seems like if I reduce power consumption, my gain is increasing. Normally, for getting everything, you have to increase power. This is one of the few things where you get higher gain with lower power consumption. Okay, but these expressions are all true as long as the transistors are in saturation. If it's not in saturation, then the relations will change. As it turns out, if you keep on reducing current, then the transistors will eventually go into sub-threshold, provided you have biased it properly, and then this GM over GDS ratio kind of remains constant. So till the transistor it goes into saturation, you can get as long as the transistor remains in saturation, you can get some leverage by decreasing I naught. That's fine, but still you'll get limited by GDS because ultimately it's not as if you can push I naught to 0 and get infinite gain. That's not going to happen. So there will be some gain limitation, and the gain limitation will come because of the intrinsic gain of a transistor, right? So it will effectively by GM over some GDS, right? So the question that we are now asking is that if we are limited by the intrinsic gain of the transistor, is there a way of getting rid of that problem? Okay. So now let me simplify the problem down and say, let's take one transistor. And let's say it is biased properly and all. Let's say it's biased with this structure. Okay, so I shouldn't say do this. I probably should. I mean, you assume that this is biased. We know multiple ways of biasing with a constant current source. So you can choose your favorite one. Right? You can choose a current meter on the top. You can choose the one that we just talked about. So let's do this. Maybe the eraser not working. Okay, and if we consider the incremental model, in the incremental sense, this is what? In the incremental sense, this is grounded and this is Vi. Correct? So now the question that we are asking is, or rather the problem that we are facing is, the current, the GM Vi current that is flowing out flows into its own GDS. Correct? And you have some load connected here. You have some active load connected here. Maybe that load is a PMOS or a PMOS load or something like that. Okay. So which essentially means that you have some R out of some configuration on top. Correct? So this is constant voltage, let's say, and don't bother about whether this will be biased properly or not, because we know that it will be biased using some negative feedback loop. Okay, so now the question is, we are trying to maximize the gain that we can get from this structure, and we see that if I connect these two directly, the gain will be GM minus GM Vi R out parallel RDS. Okay, so what is the root cause? The root cause is if I assume that R out is much higher than 1 over GDS, right? So if R out is much greater than 1 over GDS, then essentially your gain is minus GM over GDS. So in other words, physically, if we have to understand this essentially means that all the incremental current, or the most of the incremental current, is flowing in this loop, right? Because RDS will be much smaller than R out, RDS will be loading the GM and not the out, right? So you'll be getting this gain. Fine. So the question is, how do I increase the gain now if it is only going into its own internal resistance, right? If the incremental current is only going into its own incremental resistance, then how do I increase the gain? Okay. So the question that we are so the modified question that we are asking is, then can we do something, because we cannot really get rid of this own internal resistance. Can we, the only terminal that we have access to now is the drain. So can we put something here? Can we put something here so that the resistance increases, right? Now or rather, can we put something here so that this incremental current doesn't flow into GDS, but flows into whatever we are putting, right? So if this incremental current doesn't flow into GDS, which means GDS is not loading the GM anymore, right? Do you agree with that? Okay. So the problem statement now gets redefined as what should that box be so that the incremental current doesn't flow into GDS. Okay. Fine. So now let's look at it from the lens of resistances. So if the incremental current has to flow into this box and not here, then can you comment on the input resistance of that box with respect to the GDS or RDS? Yeah, right. So the input impedance is Rin has to be much lesser than 1 over GDS or RDS. Correct? Fine. So do you know any single transistor structure where the Rin is low with respect to RDS? Source of an NMOS, right? So in this case, NMOS. So fine. So let's put a source of an NMOS there. Let's sketch the incremental first, then we'll do this biasing later. So let's put the source of NMOS. You have this RDS here. And this is also biased using some voltage divider or some voltage source or something, okay? So the looking in impedance here is 1 over GM. Let's call this M1, let's say M3. 1 over GM3. So if you make 1 over GM3 less than this RDS1, or GM3 times RDS1 much greater than 1, then the incremental current will choose to flow into M3 and not into RDS1. Okay. So if all the incremental current flows into M3, then it seems like we have prevented the loading of RDS1, right? But when the incremental current flows through M3, it also has its own resistance. But when the incremental current chooses to flow into M3, it only can come out of the other side, right? Because it cannot go anywhere else. So this current will also be GM times VI, right? Okay. So now the question that we need to ask is, if this is the new output node, what is the incremental voltage that is going to get generated? Okay. So which essentially means that the question that we are now asking is, I know the short circuit current. The short circuit current is GM times VI, or minus GM times VI in the direction that I have shown. Now I have to find out what is the incremental output resistance looking from that, right? So this resistance is R out of some stage, I know, right? But the key thing is to figure out what is the resistance looking down, right? So what is the resistance looking down? We have seen this structure in multiple contexts. Tell me what is the resistance looking down? No. Why? Right. So it will be basically this RDS1 and RDS3 will come in CDs anyhow. So RDS1 plus RDS3 plus the intrinsic gain of M3 times RDS1. So GM3 RDS3 times RDS1. So which term dominates? So this term dominates because RDS1 is multiplied by a gain term, right? So this becomes approximately becomes GM3 times RDS3 times RDS1. Okay. So again, I mean, this is a very useful term to by heart. So just by heart this term so that, I mean, you don't have to write KVL, KCL for every small piece of circuit every time. So now what is your opinion about this new resistance looking down from V naught? Is it high with respect to the case in which M3 was absent, or is it low for similar order? It is high, and it is high by an order of magnitude because the resistance of RDS1 is getting multiplied by the intrinsic gain of M3, right? So you're increasing the output impedance. So this is another way of increasing the intrinsic gain of the transistor, of the structure. You can assume that this is almost like a case in which if you don't know what is inside your architecture, this would seem like you have a transistor whose short circuit current is GM times VI, and its output resistance is GM3 times RDS3 times RDS1. Right? It would seem like a box. You don't know what is inside the box. If you only look at the gains and the short circuit currents or the Norton equivalent, it would seem like it's a common source amplifier which has a GM of which is equivalent to the GM of M1, but it has an output resistance which is RDS of the transistor times some factor, right? So effectively, you see that putting a structure on top. This is a cascode transistor. M3 is a cascode transistor. Putting a cascode transistor on top increases the output resistance of a stage. Okay, so that helps a lot in naturally it helps a lot in increasing the gain. Okay, make sense? Any questions about this? Okay. So just like you can do a cascode on the NMOS side, you can also do a cascode on the PMOS side, right? So you can have structures like this. So this, let's say this is M1. Let me now rename this transistor. Let's say this is M2, M3, M4. So the M1, M3 is a cascode on the M3 is the cascode transistor that is shielding the M1 transistor or increasing the gain or increasing the output impedance looking down. M4 is the cascode transistor that is on the PMOS side that is increasing the output resistance looking up, right? Looking into the drain of M4. Okay. So, and if you want to bias this, you can bias this with. We have seen multiple ways of biasing. You can choose your favorite one and bias. Okay. So, what is that? I mean, then why should everybody not do this? Every time it looks like it's a, win-win situation, right? I mean, I'm not really burning any extra current, and I am getting a high intrinsic gain, essentially. So do you see any downside to this? Right. So the output voltage swing will be a problem because earlier in this structure, in the left structure here, so the output voltage V0 could have got could have gotten higher, almost close to VDD, right? One V overdrive near VDD. V0 could have gotten that much. And V0 in this case can go down one threshold voltage below the gate voltage, right? So it's almost like a full range that it can. It's almost like swings peak to peak. I mean, it almost has a full rail to rail swing that is available. But in this case, on the higher side, as you can see, that now you have to honor the saturation condition of not only M2 but also M4, right? So what is the maximum that V0 can go to? So firstly, you have to honor how much? This has to be one V overdrive at least. And this guy also has to be one V overdrive at least. And if you keep a V overdrive of 200 millivolts approximately, so earlier you were losing about 200 millivolts just for biasing. Now you are losing 400 millivolt for biasing. Okay. Similarly, on the bottom side also you will lose because of the MC transistor, right? MC transistor will also have an overdrive of let's say 100 200 millivolt. You will lose another 200 millivolts. So the big problem is if you have to if you want higher swing, then this type of structures will not suffice. Okay, but there is some redemption because I think not in this regard, but I had posted an assignment, last assignment probably, or the one before that, there was one problem that you might have noticed. So let's say I have two stages. So now I'm drawing only symbolic. So let's say I have only two stages and put in negative feedback. Let's say this is VI, and let's say this has a gain of so this has a gain of 100 and this has a gain of 100. AV1 and AV2 are 100. Let me put 10. I mean, numbers become manageable then. Okay. And let's say VI swings. VI is VP sine omega t, so which is 100 millivolt, or let's say 200 millivolt sine omega t. So what is the peak to peak swing of VI? 400 millivolt. Okay. So let's say this is V0 and this is V01. How much will V0 swing by? Four volts. Why? V0 will swing by 10 times of VI. Why? So let's assume V01 will swing by. Let's forget about V01. I'm asking V0. How much will V0 swing by? What will be the gain between VI and V0? Why? Not the open loop gain, closed loop gain in this structure. Approximately one, right? This is the unity gain feedback, right? So there will be some steady state error, but approximately the gain is one because you cannot sustain a finite input voltage across an error amplifier. Because if you have a finite input voltage, then the gain, output will increase. And since this is a negative feedback, this will come and decrease again, right? So it will keep it in the direction that forces the error to reduce. Negative feedback, okay? So which essentially means that V0 will also be approximately equal to 200 millivolt sine omega naught t. Okay, so any questions on this? Okay, so VI swings by 400 millivolt. V0 also swings by 400 millivolt. How much does V01 swing by? So what is the gain of the second stage? 10. So how much should the input swing by? If the output swings by 400 millivolt? 40 millivolt. One of the input terminals is grounded. The other terminal has to swing by 40 millivolt. Direction? Reverse, right? So essentially this reverses and this will be 40 millivolt. Okay. So what are you observing? The observation is the output is swinging by 400 millivolt, but the input of the first second stage is swinging by 1/10 of that. Okay. So which essentially means that if I have to choose to use this Cascode configuration, because I know these are all some sorts of common source amplifier or differential amplifier or something. If I have to get, let's say I want to increase the gain of this structure without compromising the signal swing, whether the first stage should have a Cascode or the second stage should have a Cascode, or both can have a Cascode? Or is there a trade-off? With respect to signal swing. Why?
For maximum swing.
The Cascode reduces swing, right? Because it cannot go all the way up and down. Because the moment you put a Cascode, you are losing one V over L, isn't it? So essentially you have to find out what is the algorithm then. The algorithm is if the signal swing requirement is high, you cannot put a Cascode. If the signal swing requirement is low, then you can put a Cascode. So in this case, signal swing requirement is high at V0 or V0 V0, right? So which means that whatever is driving V0 should not be a Cascode. Right? So whatever, but V0 is only swinging by 1/10 of V0, which means V0 first stage can be a Cascode. Okay? So that is why in many two-stage or multi-stage amplifiers, you will see the first initial stages have these Cascode structures and then subsequent stages don't, because of these reasons. Okay. By the way, one quick question: if I ask you what is the swing at the input of the first stage, what will your answer be? Is it 400 millivolt? What is the input? How do you define an input? V plus and minus, right? So difference between these two terminals, right? So if I assume if I now say that output is 400, so what is the difference? 0, right? But you cannot neglect something with respect to 0, which means if something comes out to be 0, you have to dig a bit deep. What will you do? You will have to now take into account that this loop gain is not infinite. So by the way, this will be 0 only when the loop gain is infinite, right? Because steady state error is 1 over loop gain and all. So now when it's coming to 0, you know that it's probably something second order effect or a first order effect that you are neglecting. So you go back and then figure out. So how much will be the difference? The difference will be essentially whatever approximately this is 400 millivolt ideally, but it will be divided by the loop gain. The loop gain is 100, so probably we will have 40 millivolts being at the input, right? So no, I think I made a mistake. The steady state error will be 40 millivolt, right? So approximately 4 millivolts. Sorry, the loop gain is 100, right? I'm still probably in reality. So loop gain is 100, so this goes by 400 millivolt. So divided by the loop gain approximately. So essentially, the difference between the plus and the minus terminals will be 4 millivolt approximately. Okay, so that you can also figure out from here. So you have 40 millivolt swing at this node divided by the gain on the first stage, which is essentially 4 millivolt. 4 millivolt is the difference between the two terminals, not one of the terminals only. Okay. Okay. Any questions? Okay.
So in this structure, we can put the V0 terminal at M0 drain also. Then the swing disadvantage.
M0 as in what? M1 drain. Okay. Yeah. Okay. That's a good question. So if I put V0 1 here, right? So what is? I agree with the fact that the lower part of the swing, you are very close to the minima. But what is the output impedance looking into this terminal? It's 1 over GM3 approximately again, right? Again, but I mean that okay. So which essentially means that you don't gain anything. Right? Okay. The one caveat here you have to, while doing analysis, this is only 1 over GMC, only if you neglect the channel modulation for LC. Right? If you have channel modulation for LC, then it will be something plus you have, and this is 1 over GM3 under certain constraints. But anyhow, I mean you can figure that one out. But 1 over GM3 is not a bad approximation to make. Okay. So the reason I put this structure up is that some of you, if you are interested, you can, especially the Cascode part, some of you, if you are interested in the project, you can use a Cascode transistor to increase the gain, which is a doable thing, right? It's not as if you have to, the structure that I have given, you have to stick to it, even if you are not meeting the spec. You can try to change the structure a bit. Okay. So, fine. So till now, what we have done is all the time we have assumed that we have an ideal voltage source, ideal current source. Ideal voltage source is very easy to get. You get to the market, take a double A battery, it will give you 1.8 volt, 3.3 volt and all. But it's not very easy to procure ideal current sources. So what we essentially said that we will in this course, we cannot cover how to make a very good current source on chip, right? You can make decent, decently behaving current sources by doing some funky stuffs. But let's assume that a current source is available, but we are trying to mirror the current from one branch to another. And the question that we are asking is that what is the best way to mirror? Right? Till now, we have assumed that mirror, if you just make the VGS same and W by L same, then the mirroring is perfect. But in essence, it's not. And we know why it's not, right? For example, let's say I have a current mirror. Say this is some VDD or some V0. So if I neglect channel length modulation of M1 and M2, right, then obviously the current in the left and the right branches are always the same. This will also be I0, because if the W by L are same and the VGS are by, in this case same, threshold voltage same, then obviously there is no other way but I0 to be in the right and the left branch to be identical. However, if I consider channel length modulation, then will it be identical? It will be identical only under certain constraints. What are the constraints in which it will be identical? Same? Okay, lambda is same. I give you that. Mu and Cox, VT, lambda, all are same. I want the currents in both the branches to be identical. So what constraint should it be? Right. So the drain voltage should be same. Because now your transistor, if you are not neglecting channel length modulation, which means the current is a function of both VGS and VDS. Right? So lambda VDS terms will come. So since the current is now a function of, or rather it's always a function, but now if we want an increased accuracy in the current mirror, we should also take into account whether the VDS of the both sides are identical or not. So the current in the right branch will be exactly equal to I0 only when V0 in this case, this voltage will be equal to this voltage. Right? So when V0 will be equal to the VGS of M1, then your current will be exactly equal to I0. Okay. So if V0 is equal to VGS of M1, so let me call this. Call this I1 and that is I2. Then I2 is equal to I1. Okay. So let's say VGS of M1 is equal to 2 volt. Okay, and threshold voltage 1 volt and so on, what we have been taking. So under this condition, if this is 2 volt and V0 equal to 2 volt, this current will be whatever it is. This current will be I1. Okay. So now, so this is one aspect. The second aspect is the right branch V0, we cannot expect it to be constant because ultimately there will be some signal, it will go up and down, right? So let's say this from V0 to be 2 volt, it goes to 3 volt. So let's say 2 volt is mean, it can go from 3 volt to 1 volt. This is a signal swing that you can have on V0. Okay. So can you comment on approximately how much will I1 change? So let's say V0 goes from 2 volt to 3 volt. How much will I1 change, right? Approximately. Expression, obviously I haven't given you all the. Yeah, lambda times that delta VDS, right? That is correct. But can I also say that this current, the output voltage change is 1 volt. So if I say that delta VDS is 1 volt, the current change is GDS times delta VDS. Right? No, I cannot say that. Why not? What is the definition of GDS? GDS is del IDS, del VDS. Right? So del IDS is GDS times del VDS. Right? So then can I say that if the output changed by 1 volt, then del IDS will be GDS times 1 volt? I can say that, right? So similarly, if the output changes by 1 volt on the bottom side, right, it goes from 2 volt to 1 volt, then delta IDS will be minus VDS times 1 volt, right? So if the signal swings by 2 volt, the current will be I1 plus minus VDS times whatever the swing is, right? Okay, makes sense? So, which essentially means that if GDS is not high or not low in this case, you can have a lot of change in current mirroring, right? And in some applications, it might not be acceptable. Okay, so which essentially means that we have 2 things to honor. One is in a current mirror, the first thing that we have to ensure is that VDS of M2 remains approximately equal to VDS of M1. Without that, the fundamental mirroring will be incorrect. And second thing that we have to ensure is our output resistance of the current mirror has to be or tends to infinity. Has to be very high. Okay, make sense? Okay, so now let's attack it from the perspective of the first condition, right? So because V0 is not in your control, V0 can move up and down. Okay, since V0 can move up and down, this structure obviously, whatever you're seeing in your screen, is not particularly feasible. It's not particularly feasible in many applications. So let's spend some time to figure out what are the other possible options. So which essentially means that I have to put something here again. So your V0 goes here. So I have to put something between V0 and M2 so that this voltage becomes equal to the voltage on the left. Okay. Okay, so I said that I wanted to attack it from the perspective of the first condition, but since we did the Cascode, let's attack it from the perspective of the second condition, right? So it becomes the continuity of argument will remain. So what I'm essentially saying is that let's try to do this. Let's try to make R out to be very high. right? So what is R out by definition? I mean, my R out definition is looking down from V naught, right? So if I want to make R out to be very high in the context of whatever we have done till now, what is the obvious thing to do? So what should I put in that box? Cascode transistor, right? Another NMOS. So let's put another NMOS. And fine. So we have to bias this also with some VGS3. Okay. So this definitely is increasing my R out, right? If this increases the R out, if delta VDS now changes by, let's say, 1 volt, how much will, can you comment on how much will be the delta IDS change with respect to the previous structure? Huh? It will be less of the order of? No, the delta I will be delta VDS by R out. R out has increased by what factor? Intrinsic gain of M3. If M3 gives you a gain of 10, then the delta IDS will be reduced by a factor of 10. Right? Okay. So this is good, right? So if I am not satisfied, I can put another cascode on top. And it will go down by another factor of the intrinsic gain of that transistor, right? So I can keep playing the game as long as I'm okay with the signal swing. Because ultimately, the moment you put transistors on top of each other, you lose signal swing. Okay, fine. So this is good. So it looks like we have a handle of how to tackle the second point. R out tends to infinity or very high. Infinity, which means is essentially with respect to the load that it is driving. Okay. So now, how do I ensure that the quiescent current on both sides are identical also? I have to ensure that I1 and I2 are identical, which essentially means that I need to ensure that these two voltages are similar. Same, ideally same, but we know enough by now that nothing is absolute what you want, it has to be similar. So before we answer this question of what needs to be done here, we need to understand who sets the drain voltage of M2. If we know who sets the drain voltage of M2, then I have a handle of making that voltage equal to whatever we want. So now tell me who sets the drain voltage of M2? VGS3, right? Do you agree? Right? So actually, I shouldn't have written VGS3 here. I should have written VG3. That's a VGA3, right? So if this voltage is what now for proper mirroring, what is this voltage that we want? VGS of M1. We want VGS of M1, right? We want this to be VGS of M1, right? So if we want this to be VGS of M1, what should VG3 be? For proper biasing, and assume all transistors are identical. Need not be, but assume all of them are identical. Right. So essentially, VG3 should be VGS of M1 plus VGS of M3. And if both or everything is identical, this battery should be 2 VGS of M1. Correct? Do you agree? Okay, that's good. So now the question is, how do I generate this 2 VGS of M3 or 2 VGS of M1 or VG3? One might argue that just put a resistor divider. I can put a resistor divider to get that voltage. Okay, that's not a problem. But let's say now, the threshold voltage has changed. Okay, if threshold voltage has changed, then VGS will change. Correct? So if VGS will change, then you would also expect this voltage to go up or down depending upon how the threshold voltage has changed. But if you put a resistor divider or a fixed voltage, fixed battery there, then that's not moving up and down. Which essentially means that this current mirroring will not be constant across temperature. Maybe at a particular temperature, you will get very good mirroring. But if you change the temperature, your mirroring will not be good. It might also so happen that because for those of you who have been taking device courses, you'll also know that when you make a wafer, it's not necessary that every batch of wafers will have the same threshold voltage, right? They can have a variation. Okay, so circuit designers model those as corners. So typically, we say typically let's say it has a threshold voltage of 500 millivolt. Then there will be a bell curve around that 500 millivolt, right? So everything has a distribution. Maybe the threshold voltage distribution can go from 400 to 600, right? So the corners in which it goes to higher threshold voltage, we call them slow corners, because threshold voltage is higher, so transistor is probably slowing down, and in the corners it has a lower threshold voltage, we call them fast corners. Threshold voltage is lower, transistor is probably has a more capability of driving, right? So that is the terminology part of it, but the moot point is that when you are trying to design, you have to ensure that your circuit works across corners and across temperatures. Okay, so it's quite possible that your wafer came out at a slow corner and you are designed for a nominally for a 500 millivolt corner, and you have to ensure that your across temperature also it works. It should be working at 0, it should be working at 70, it should be working at minus 40 degrees centigrade and all. So essentially, your design should be fail safe across change in wafer, on top of that change in temperature. So it might as well be that your threshold voltage is probably changing by plus minus 300 millivolt. That is also possible. So which means the current mirroring has to be accurate with respect to all these constraints that I am talking about. So putting a fixed VGS or putting a fixed voltage biasing, that's why is a particularly bad idea. Okay. Okay. So if that is the case, then the question is, what is the solution? Okay. So we want approximately 2 VGS. Let's say forget about 2 VGS. If we want 1 VGS, what is the way to generate that VGS voltage? Right. So essentially a diode connected transistor, the voltage that is generated is 1 VGS. Correct? So we know that VGS is equal to threshold voltage plus under root 2I0 by mu n C of W over L. And how do I generate this? I can generate this by simply passing the I0 through a diode connected current, a diode connected transistor. So now I want to generate another VGS. So essentially what I'm saying is, this is VGS now, but I want another VGS to be added to it. So what can I do? Pardon? I don't want to change current because the whole purpose is to mirror the current, right? Don't want to change current.
Two same branches in parallel.
Two same branches in parallel. Okay, so let's see. Okay, I have two same branches in parallel. This is also giving me VGS.
You connect that top of I0.
Want different names, right? Let's say M4. You want to connect?
Both in parallel. So the current drawn would be 2I0.
Correct.
And
so both of them will have identical VGS. Ultimately, you want to add up the VGS, right? Essentially, I want higher VGS means I'm adding up the VGS. Correct? Pardon? What will that do? Changing the length? It will increase the VGS, I agree, but will it help? Because if I am changing something with respect to M1, I have to do the same thing with respect to M2 also, because then the mirroring will not be perfect. So that is a subtext. You have to assume that we change in one is reflected on the corresponding transistor on the right branch. Okay. So changing L, I agree, increases the output resistance, which probably increases the mirroring also a bit. But you can only do practically, you cannot increase that indefinitely, right? So we are not looking for that solution here.
The gate of M1 to source potential.
Gate of M1 to the source of M4. And you will not have diode connected, is it?
Both are in this technology.
Okay, gate of M1 to source of M4. This.
From that, this is the gate of M4 is
Okay, how this is interesting. Will M1 get biased properly in this case? Right? But I understand what you're trying to do. So ultimately, so let's say instead I call this terminal, VS1. Okay. So if this is VS1, what is this voltage? VS1 plus VGS, or rather VGS plus VS1. What do we want? We want VGS plus some another VGS. Correct? If I can set VS1 to that VGS, what we want, then I should be good. Right? Okay. So how do I set VS? How do I get another VGS?
VS1 to the drain.
Right. So essentially, what we are looking for is another. So if we connect this to here, right? If we connect this to here, I mean, this will not be particularly this is not the solution I'm looking for, because simply because what you are seeing a current division here also, right? At this node between the I0 on the right branch, because now the transistor M4 is trying to get 2 I0 current. Correct? It's trying to, because ultimately the way this has been structured, this is I0. So M4 is now trying to get 2 I0 current. But we don't want 2 I0 current. How much do we want? I0. So I can get rid of one of the I0. Which I0 do you want to get rid of? Top one, right? So I can get rid of this guy. And if I resketch this, this essentially becomes let me rename the transistors. We call this M4. Okay, so this is VGS1, VGS of 1, the other becomes VGS of 4 plus VGS of 1. Okay, and you had this structure anyhow there. And what was the whole purpose of generating this? The whole purpose of generating this was to bias this the other transistor, right? Let's call this M3. Okay. Fine. This is just like a PMOS, is not a PMOS. So similarly, you can also have PMOS equivalent of this. You can have the PMOS equivalent of a simple current mirror is this. This we have done in the context of DFAM. But if you want to do the similar cascoding, so you have to put something here, put something here. Right? So this is the PMOS equivalent of your current mirror with a cascode transistor. Okay, make sense? Okay, but now the question is, this definitely will give you better mirroring. But what about the minimum V0 to keep all transistors in saturation? Right? So what is the minimum V0 that you can have? Let's take some numbers. Let's assume VGS1 is, let's say threshold voltage is 500 millivolt. And you want to keep a overdrive of 100 millivolt. Okay. So what is this voltage? $600. Okay. You want to keep a overdrive of 100 millivolt, which means, okay, by the way, you want perfect, good mirroring between the circuit and the branch on the left and the right, which means what should this voltage be? Or rather, what is this voltage in this configuration? Approximately 600, right? Great. So this is 600. Maybe I use a different color. This is also 600. So what is the gate of M3 biased at? 1.2. So what is the minimum V0? 1.1. Right? So you see that even if you're operating with a supply voltage of 1.8 volt, 1.1 volts just to bias, right? Not particularly good idea, even though you are getting very good mirroring, very good output impedance and so on, right? So as you see, the problem is if I only look into the right-hand side, the problem essentially is I am losing 600 millivolt across M2, right? So that's the problem. Sorry, I think I made a mistake. What mistake ready? So this is not 1.1 minus VT, right? Not minus V volt, right? So this is 0.7. Okay. So I am losing 600 millivolt across M2. M3 is fine. It's only 100 millivolt. Correct? So it seems like this is the causing the most of the problem. Ideally, I should only lose one overdrive, right? Ideally, just like M3, I have a VDS of one overdrive, right? That is good enough to keep M3 in saturation. But in case of M2, I am having one overdrive plus one threshold voltage, and that requirement has come because I want to mirror properly. Okay. So people have figured out ways of getting rid of this problem. And from this perspective, if we attack the problem from this perspective, things kind of become obvious, because ultimately the root cause is if I diode connect here, then this will obviously always be VGS. And for proper mirroring, I need a VGS here. That is a requirement. But if I don't diode connect, then the requirement of M1, if I don't diode connect, the requirement of VDS for M1 is only one overdrive. Correct? So this can also be only one overdrive. Right? But the question is, how do I set the current? This is all good saying that I will not diode connect, but I also have to give the gate voltage. Somehow I have to give the gate voltage. Without that, nothing will work. Which means that it has to come from somewhere. Okay. Fine. So let's see from where that it can come from. We will require this Cascode transistor. That we definitely require. So if I require a Cascode transistor on the left branch, I'll also have a Cascode transistor on the other branch, right? Because mirroring, it ensures that whatever you have on one branch, it should be there in the other branch. So this should be there. But the stuff that is absent in this is, I don't know how am I setting the gate of M1, correct? But let's say, if we are able to do this, then what is the requirement? What is the voltage requirement of this transistor, of this node? VGS plus VGS plus 2 VGS. Sorry, VGS plus overdrive, right? So 1 VGS plus overdrive, and this V0 min can be only 2 overdrive, 2V overdrive. So if we are able to manage something with this structure, then there is possibility that if the overdrive is, let's say, 100 millivolt, I can go almost 200 millivolt close to the ground. Right? Okay, so then what is the possibility? What can be done? So ultimately, I still have this. By the way, if I only connect it like this, will this structure what? No, why not? So what will happen? It's not set by any IIT, but if I just connect it like this in the lab, what's going to happen? There is no bias, so something will happen. What is going to happen? Yes. And now we know that the current source is also not ideal. It's some PMOS probably. What is off? M1, M2 are off. So I agree. Maybe M1, M2 are off. I don't know. It's floating. Gate is floating. I don't know who is driving what. So what are the possibilities? What I'm talking about the operating condition of the transistors. What might happen? And given that the current source is also, let's say, a PMOS. Take a shot. No current will flow, which means what? Which means no. What's going to happen to the current source? It's a non-ideal current source now. It's a PMOS current source, let's say. So what's going to happen to that? Why that will be open? So assume that the PMOS is like this. So maybe it's so PMOS, let's say, is biased like this. Okay. So now tell me what's going to happen. We're just throwing terms. You are just throwing terms. What is going to go below threshold? Why? Because VGS is constant, right? VSG of the PMOS is constant. So why should that? Drain voltage of? Right. So this drain voltage of this PMOS will increase. Because if we assume that this is not M1, M2, this is, I mean, floating can be anything, but let's assume that is zero. If that is zero, then this current source is trying to push in current and the bottom circuit is not able to accept it. Right? So that voltage, this drain voltage will increase, and it will increase till the PMOS goes into linear, and it essentially shuts out any capability of pushing current. Okay. It will still be on, but in linear region, but it will not be able to push in current of I0, right? So that's not going to happen. Fine. So let's assume that we have this current source here. Okay. So now we need to ensure that this voltage is still 1 VGS. Okay. So how did we, if you recall, initially when we came up with the diode connected transistor equivalent, right? How did we argue? We argued that it's a negative feedback. We are observing the drain voltage. If the drain increases, it's giving me an information. What is the information it's giving me? That I have to increase the strength of the transistor. I have to increase the gate voltage to accept that current. So I connected drain to gate. You recall, like ages back when we were initially doing negative feedback. Now today is the last class. Now tell me, how do I proceed with the same argument? So what am I going to observe to understand whether I have to observe some voltage. Which voltage would you like to observe? So there are only two places to observe, right? And the drain of M1 or drain of M3. Which one would you want to observe? Drain of M3. So fine, so if drain of M3 is increasing, what information is it giving you? Can you?
The lower circuit is not working.
Okay. So what should I do to M1? Should I increase the strength of M1 or reduce the strength of M1 if the drain of M3 is increasing? I need to increase the strength of M1. How do I increase the strength of M1 without changing W by L? Increase voltage, increase VGS. Right? So again, drain is increasing. The information that I am getting is the drain voltage of this is increasing. The action that I need to take is increase the gate voltage of gate to source voltage of M1. So what is the obvious thing to do? Connect this, right? So connect this. Okay. Okay, fine. What about the cascode transistor voltage as VGS plus V overdrive? So this is likely not obvious. So let me write it out. So this voltage that is VGS plus V overdrive. This is, if I break it up, this effectively means threshold voltage plus 2 V overdrive. Correct? I'm assuming all transistors to be identical. So if I break it up further in terms of if I write out the expression of V overdrive, so this becomes 4 times I naught by mu n C of 4 times 2 I naught times mu n C of by W by L. Right? So this seems like a case in which I have put in a current of I naught into a transistor, or I have put in a current. Yeah. So if I sketch it, if I rewrite it in this form, 4 goes to the denominator. It seems like this is the case in which I have put in a current source of I naught into a transistor whose aspect ratio is W by 4L. Right? So which essentially means that really I have a case in which this is W by 4L. Then this will be VTH plus 2V overdrive. Okay. And then what you do, you go ahead and this. Okay. So if you do this, what will be the minimum output voltage that you can sustain? 2V overdrive, right? Or the example that we took, it was 200 millivolt, not like 600 millivolt or 700 millivolt. Okay. So that's why this is called a wide swing current mirror. Right? Okay. Any questions? Output impedance remains the same because both transistors are in saturation, right? Okay. So RDS of M2 times the intrinsic gain of M4. Output resistance doesn't change, but the the allowable swing increases. So these type of configurations are quite popular when your supply voltage is squeezed down. Okay.
So this expression we are using in direct connected case, but here it is not directly direct connected.
Direct connected is a special case. It need not be, right? So let's say I have something like this. Right? So what is the current? Current is I naught is still mu n half mu n C of W by L VGS minus threshold voltage whole squared. And if I flip and write, it will be the same expression, right? Expression won't change as long as the transistor is in saturation. Okay. Okay. Any questions? Okay, fine. The only other stuff that we didn't do, and which is kind of we should know, but not that relevant in today's architecture, but just for the sake of continuity, is the fact that in an NMOS transistor or in a PMOS transistor, we have kind of always assumed that the body is connected to the source, right? Because we have kind of neglected the body terminal all the time. But that's not the case actually, because ultimately the wafer in which you are building your transistor has a single body of P. So essentially all the NMOS transistors have a single common well in it sits in. So you cannot really say that one NMOS transistor has a different body voltage and the second NMOS transistor has a different body voltage. So essentially your NMOS transistors will all sit here. And your PMOS transistors will also be on the same well, but because a PMOS requires a separate body, right? It requires a N-type body. So generally we give it an N-type tub, and then you have P plus, and this is you do. And if you want another PMOS transistor, you can give it a separate tub. So PMOS transistors in general can have its own body, but NMOS transistors in principle doesn't. I mean, in most cases doesn't. But there are some processes in which they allow separate bodies for NMOS transistors. Those are called triple well processes. But anyhow, I mean, in more generic sense, you cannot have a separate body for a NMOS transistor. So which essentially means that if you are looking at the Cascode transistor, right? These are biased. So in case of so let's assume this is M1, this is M3, or M3. Okay, fine. So let's assume this is M1, this is M3. Okay, and let's say this is V0, which is this V0. This is grounded, which is this ground. Okay, and the body is also connected to ground. So let's say this is a P plus, this body is connected. This is a drain of M1, this is a source of M3, so these two are connected, right? But what is the body of M3? It is also at ground, right? So the body terminal is grounded in both cases. Okay. So the key thing that happens is the source to body voltage or the body to source voltage of M1 is 0, but the body to source voltage of M3 is not 0. Okay. Because of that, the threshold voltage changes, because threshold voltage is also a function of how much, whether you have, threshold voltage is essentially a function of how much charges you have and what is the distribution of the charges in the channel. Okay. So because now there is a reverse bias junction around this, right? Because this voltage is higher than ground, the N terminal is at higher than ground, and the P terminal is at ground. It's a diode where this is higher, this is high positive, and this guy is grounded, which means you have reverse bias PN junction. In a reverse bias PN junction, you have depletion region. So essentially, the charge profile changes. Because the charge profile changes, the threshold voltage changes, right? So in a Cascode transistor, that's why you will see that the threshold voltages of M2 and M4 are not particularly identical. As it turns out, if you reverse bias that PN junction, the threshold voltage slightly increases. So for the same current, the VGS of M2 and the VGS of M4 will be slightly different. But as long as you bias it using these diode connected devices, you are good. You don't have to bother, because whatever happens to the left side happens to the right side also. That will be a problem if you use only a fixed resistor biasing or fixed voltage biasing. Okay, so that is not a problem. But the other issue that happens is because threshold voltage changes, and you also see that this node swings, right? This node can swing if the current changes. If the current changes, this node swings, and because the threshold voltage also now depends on VBS, which means the threshold voltage also changes as the current changes, right? So which essentially means that the incremental model changes. right? If the signal swings and it changes the threshold voltage, and change in threshold voltage also will cause some change in incremental current, which means it affects the incremental part of the circuit also. And the way that is modeled is this. So this is source, this is gate, this is drain. So this is GM-VGS. So that structure is modeled like putting another incremental current source, which is GMB, where B stands for body times VBS. Okay. And you have this GDS and all capacitors are anyway present. Okay, so I made a mistake here. So this should not be. No, this is fine. Okay. So the other thing that you need to note here is that the body in this case is a separate terminal. Body is not with respect to ground. Okay. So CDB goes in the body, but body is in general grounded, so it's not a problem. Okay. Any questions? So don't worry, no questions will come from this. So this is just for continuity. If you go out and ask that, I don't tell people that I don't know about body effect, that doesn't reflect very good on IIT Kanpur. So just to ensure that you guys know what this is. Okay, but I'm pretty sure you have read about this in far more detail in any device courses. Okay. Any questions before we stop? Okay. So we can wrap up the course here then. Thank you for your attention and thank you for coming.